The second last lesson is going to discuss properties of quadrilaterals. Now, in grade 9, we talked about the different types of quadrilaterals, looking at the properties of each one, discussing whether a rectangle was a square or a square was a rectangle and things like that. But it just touched basically on the main properties of quadrilaterals. In grade 10, you learn how to verify or how to prove that a quadrilateral is a certain type. So in the first part of this note, we're just going to briefly go through the main properties of the quadrilaterals that you're expected to know, and then we'll talk about how to prove certain properties. So the first shape obviously is going to be a parallelogram. We've noticed that we have two sets of parallel lines. Reminder that the arrows mean that the lines are parallel. So the single arrows mean those sides are parallel to each other, and the double arrows mean those sides are parallel to each other. And then the lines mean that the sides are equal in length. So the single lines mean they're equal, and the double lines mean those opposite sides are equal. So a parallelogram is what we call a quadrilateral when there are both pairs of opposite sides which are parallel. How do we prove that sides are parallel? Let's just think about it really quickly because it's going to be something that you're going to have to do when you're looking at these questions. As soon as you see the word parallel, your first reaction should be, okay, I need to make sure that the slopes are equal. So the way to prove parallel lines is to prove that they have equal slopes. And if the slopes are equal, we know the lines are parallel. The second shape is a rectangle. And the rectangle's main property is that it's a parallelogram and also adjacent sides or sides that are next to one another. This word here means beside each other. Beside each other. So the sides that are adjacent are also perpendicular. So basically it's a parallelogram with right angles. So the way to distinguish between a rectangle and a parallelogram is the fact that those sides are perpendicular. How do we prove that sides are perpendicular? As soon as you see the word perpendicular, that should tell you we're going to prove that the slopes are negative reciprocals. Anytime you're looking at parallel or perpendicular lines, you're calculating the slope in order to prove that's the case. So the slopes are negative reciprocals. This is pretty messy, sorry guys. And that's going to prove that they are in fact rectangles. Third one being a square. Thinking about these quadrilaterals, notice that each one is like the shape before it but adds a different property. That distinguishing property is the one that you want to prove to show that it is in fact a square. Okay, so if you're proving that it's a square, you would have to show that the sides intersect at a right angle, so the slopes are negative reciprocals, and also that the sides are all the same length. So there would be two things in this case you would have to prove. Next we have a rhombus. Now a rhombus is basically a square that has been tilted at an angle. R-H-O-M-B-U-S. That's supposed to be an O. Oops. So a rhombus has pairs of opposite sides that are parallel and the fact that all the sides are the same length. So is a square a rhombus? The answer is yes, because a square has opposite sides that are parallel and also all the sides are the same length. So when you think about how to prove that a shape is a rhombus, the most important part is that the sides are the same length, in which case you'd be using your AB squared formula to show that. A trapezoid is a four-sided shape where there's one pair of opposite sides that is parallel. So trapezoid. So there's one pair of opposite sides that are parallel. Again, parallel sides mean equal slopes. That's the way that you would calculate those slopes to see that the two sides are parallel and to see that it is in fact a trapezoid. Keep in mind, trapezoids might not always look like that. They might have a fourth side that's almost straight up and down. So it might not always look like the typical trapezoid of the building blocks we used in elementary school. You might have different shapes. As long as there's two sides that are parallel, it still counts as a trapezoid. So for example, that could be a trapezoid as well. Finally, we have a kite. And the thing about the kite is that the two sides that are next to each other, the adjacent pairs of sides, are equal in length. So we have these two sides that are equal and those two sides that are equal. So in order to prove that a shape was a kite, we'd have to prove using the length of a line segment formula that the two adjacent sides were equal in length. So let's do some examples of how to prove these properties. In this note, I'm not necessarily going to go through and finish every single question with you. Some of these questions can get a little bit longer, but I do want to explain how to go about solving each one so that you feel comfortable attacking each type of question in your homework. Example 1 says verify that quadrilateral ABCD is a trapezoid. So remember, a trapezoid has one pair of parallel sides. From the picture, it seems that AD and BC would be the two sides that would be parallel. So in order to prove that it's a trapezoid, we have to verify that those two slopes are equal. So thinking of trapezoids, we're going to think trapezoid, parallel sides, slope. Anytime you see parallel or perpendicular, you're going to calculate the slopes. So our slope of AD can be calculated by doing rise over run, 1 minus 2 over 1 minus negative 1, which is negative 1 over 2, or negative 1/2. And the slope of BC is negative 2 minus 1 over 2 minus negative 4, which is negative 3 over 6, which also reduces to negative 1/2. So these two slopes are equal. Now, the important part about the quadrilaterals questions, and when you're verifying certain properties, is the conclusion, because that gives you another mark or two in the question. It also sums up what you've done. It validates the work that you've created in the question. So in this case, we have to make a conclusion that proves it's a trapezoid based on the calculations that we've shown in our question. So what we're going to say for our conclusion, I'm going to put it in red because I feel like it's really important that you remember how to do this. We're going to say, since the slope of AD is equal to the slope of BC, so that's what we proved, therefore AD is parallel to BC and ABCD is a trapezoid. So we're saying what we did, what it proves, and our conclusion. Example 2 looks at the midpoints of a quadrilateral, and I'll show you something briefly in class this week, a demonstration of what happens when you join the midpoints of a quadrilateral. It's pretty neat. We're going to look at the 4 points given in this question, and we're going to plot them on a graph. So negative 4, 2 is right there. Make sure you label your points with their coordinates as well. So A is negative 4, 2. B is 2, negative 5. So right down there. C is 7, negative 3. And D is 1, 5. There we go. So we're going to connect those vertices to make our quadrilateral. Do the best I can here without my ruler. So we're supposed to calculate the midpoint of each of those sides and join them to form a new shape. So let's figure out the midpoints of each side. The coordinates of the midpoint of AD are the average of the x coordinates and the average of the y coordinates. So we have negative 3 over 2 and 7 over 2. It's okay if we put those into decimals, that's not a big deal. So negative 1.5 and 3.5. So that shape is going to be right there. Corner of the new quadrilateral will start at that midpoint. It says we're going to form a new quadrilateral EFGH. So we'll label this point E. Next, the midpoint of DC is going to be the average of the x's and the average of the y's. So 8 over 2 is 4 and 2 over 2 is 1. That's the coordinate of point F. So 4, 1 is right there. My line's a little bit off, but that's okay. Now we're going to calculate the midpoint of the line segment BC. Which is the average of the x's and the average of the y's. So 4.5, comma, -4. We'll call that point G. So 4.5, -4 is approximately right there. Again, my line's a little bit off, that's okay. Point G. And finally, the midpoint of line segment BA or AB is the average of the two x's and the average of the two y's. So -4 plus 2 divided by 2 and 2 plus -5 divided by 2. So -1 and -1.5. We'll call that point H. So let's plot point H, and then let's join those midpoints to form a new quadrilateral. So 1, -1.5 is approximately right there. That would be H. Here we have F, G, and E. So let's connect them and form a new shape. It's not the best sketch out there, but we've got an idea of the shape that it forms. And this is actually the case with any quadrilateral. If you take the midpoints of each side and you connect them, it's going to form a new quadrilateral in the inside. And that shape is actually going to be a parallelogram. As you can see, the two opposite sides do look like they're parallel in this shape right there. And that's actually what we're asked to prove in section C. So let's flip the page and let's go to section C, where we're trying to prove that a parallelogram exists within the midpoints of this quadrilateral. Now, thinking about a parallelogram, we know that the characteristic of a parallelogram is that opposite sides are parallel. As soon as we hear the word parallel or perpendicular for the matter, we're going to want to calculate the slopes. So we're going to use the coordinates of our midpoints. We're going to use point E, point F, point H, and point G to measure the slopes of those sides to see if they are in fact parallel. It's really important that we make sure we're using the right coordinates together. So for example, you're going to calculate the slope of F to G, but not F to H, because F to H is not a side in that parallelogram, it's across the middle, that's a diagonal. So you're going to go F to G, G to H, H to E, and E to F. So let's do that on the next side of the page. So we're going to take a second to copy the coordinates from the previous page. And the next thing that we need to do is we need to calculate the slopes of each of the lines. So we're going to go E to F, F to G, G to H, and H to E. The slope of E to F, don't forget your little letters at the bottom, is the rise over the run. So 1 minus 3.5 over 4 minus -1.5. So we have -2.5 over 5.5. I understand this looks very messy. There are decimals and they're in the fraction. So it's not something that we want to have. We don't want to have decimals in our fraction. It doesn't mean that you've calculated it incorrectly. It just means your coordinates weren't integer answers. So how could we get rid of decimals in the fraction? Probably one of the ways you would think would be to get rid of the 0.5s by multiplying by 10. So we can multiply that by 10 and get -25 over 55. Then we would have to reduce the fraction to lowest terms. Quickly, a little hint is that if you have 0.5s you're trying to eliminate and you don't want to be multiplying by 10 and then reducing, you can also just double the fraction, because doubling would also serve to eliminate the decimals. If you multiply the top and the bottom by 2, you get -5 over 11, and that's already in lowest terms. So it's always a quick tool to have in your back pocket. If you see that there's a 0.5 you need to get rid of, you can also just double both sides and that works too. So our next step is to find the slope of F to G. If you would like to compare the ones next to each other that you think would be equal, that's also fine. So you could try E to F and then G to H if you wanted to work it that way. I'm just going to go in order just because it'll keep me organized. So F to G, rise over run, -4 minus 1 over 4.5 minus 4 is going to be -5 over 0.5. Again, I'm going to take the shortcut and I'm going to double the top and the bottom to get -10 over 1 as my slope. So the slope of the next line segment is the line segment GH, and we are hoping that we'll get the same slope as we got for E to F. So -1.5 minus -4 over -1 minus 4.5 is going to be 2.5 over negative 5, which when you double that fraction is also equal to negative 5 over 11. It's the same thing as what we came up with. That shows those two lines are parallel. So the slope of GH is also negative 5 over 11. I'm going to sneak the final calculation down at the bottom of this question there. I'm sorry, I'm a little bit short on space. Slope of H to E is the rise over run. So negative 1.5 minus 3.5 over negative 1 minus negative 1.5. So we got the same thing as what we did last time we did this calculation. We have negative 5 over 0.5, which when we reduce it equals to negative 10. So that's the same as the slope of FG, and we have GH and EF that also both have the same slopes. So we can conclude that it is in fact a parallelogram. Now I am definitely short on space in this question, but I'm going to sneak a little conclusion right over here. Let's say since the slope of EF is equal to the slope of GH and the slope of FG is equal to the slope of HE. Therefore, that means that quadrilateral EFGH is a parallelogram, and I'm going to be very, very lazy with the word parallelogram, if it's okay with you guys. Parallelogram. There's my abbreviation. Just a conclusion that it is in fact a parallelogram. So the final question in here looks at the properties of a rhombus, and it asks us to prove or verify that the example given is that of a rhombus. So we're not going to do every single calculation here. We're going to do one or two of them just to show you how they're going to work, but I want to talk about how to go about these questions. Verifying that we have a quadrilateral that is in fact a rhombus will mean that we're trying to verify that the side lengths are all equal. So as soon as you see a rhombus, you should think equal sides, and that means you're going to use your length of a line segment formula. So equal sides, we're going to use the AB squared formula. I'm going to do one length with you and then assume that you guys know how to do the rest of them. There's not enough space in this little sheet that I have here that I can fill them all in with you, but all the answers should be the same if it's a rhombus. All the side lengths should equal the same thing. So let's do PQ squared. PQ squared is equal to the rise squared minus the run squared. So 1 minus 3 squared, or 3 minus 1, the same thing, plus 0 minus 3 squared. So rise squared plus run squared will give you the length squared. So negative 2 squared plus negative 3 squared is actually just 4 plus 9. So PQ squared is equal to 13. So that means that PQ would be the square root of 13. That's how many units it would be long. You don't even need to figure out the square root of 13. I mean, you could in your head, you could say, okay, if I did 3 times 3, I'd get 9. If I did 4 times 4, I would get 16. So 13 is probably somewhere in between 3 and 4. You could work it out and get 3.6 or 7. But you don't need to find the exact decimal answer because all of the square roots should be the square root of 13. Every single length should give the same answer underneath the square root sign. So if you were to work out QR and RS and SP, and they all equal root 13, okay, obviously you're going to solve this properly, but I'm showing you the answers, then you're going to give a conclusion. Your conclusion is going to say, since PQ is equal to QR, which is also equal to RS, which is also equal to SP, therefore, PQRS is a rhombus. And you might think to yourself, how come we don't need to prove that the sides are parallel? Well, even if it's a square, the sides are still parallel. So regardless, a square is still an example of a rhombus. So proving that the side lengths are equal is all it takes for this question. In part B, it asks you to verify that the diagonals bisect each other at right angles. So let's talk about what that means, because that's an important kind of question that you need to know how to do. When you see the word bisect, that means to cut in half. So think about the perpendicular bisector. We figured out that that perpendicular bisector, or the right bisector, went through the midpoint. right? So we calculated the midpoint when we were bisecting. Same thing goes here. Okay, in this case, they want to know that they bisect each other, and on top of that, that they're bisecting at right angles. So there are two parts to this question. Cut in half means they go through the midpoint. That means the midpoint of the first one should be equal to the midpoint of the second one. If the midpoints are equal midpoints, that means they bisect each other. So you need to remember that if you're ever asked about bisecting, then you need to figure out the two midpoints and compare the two of them. The second part of this question says, does it bisect at right angles? So the right angle part means that they're perpendicular lines. And to solve for perpendicular lines or to prove them, you're going to calculate the slopes. And if you're comparing the slopes and they are negative reciprocals, you'll know that those two lines are perpendicular. So I think what we're going to do is we're going to take this question up together on Monday if we have time with our judging. Otherwise, we'll take it up at the very end of the period. And I want to go over the solution with you to make sure that you're clear on how to approach this question. I think this is probably the only one that might cause you some difficulty of the questions in the note. So try the homework questions on quadrilaterals. Give it a start. We'll have some time in class hopefully on Monday. I'm not sure how the judging is going to go and what the time frame will be, but you're more than welcome to sit there and do some practice questions while they're in our room judging our stuff. And we'll talk more about this tomorrow. Final lesson is going to be on Tuesday, and it's the equation of a circle. So that's going to be the end of our unit. So we'll leave it here for today, and I hope you guys have a good weekend.